everyone, Katrina here. Today we're going to be talking all about curve sketching and optimization techniques. Please subscribe for more videos and be sure to watch to the end to see our full example unfold. So we're going to consider some function f of x equals to x to the power of 5 minus 2x to the power of 4 plus 3. And let's go through all the different elements of DISCA. So starting with the D, who remembers what D is? Right, it's our domain. So the first thing we can see here is we should classify what type of function this is. Is it rational? Is it root? Is it polynomial? Well, this is actually a beautiful function and it is a polynomial. So since it's a polynomial, we know that by definition of polynomials is that it has no restriction on its domain or on its range. So why don't we actually go ahead and write our domain and range. So we can see that x is an element of the real numbers using our nice set notation, and writing that in French there, our range, we have that y is also an element of the real numbers. So that's really nice to know that when we're going to be sketching this, that we don't really have to worry about any restrictions on our numbers. Okay, let's go ahead and do the I. I is our intercepts. So let's start with our y-intercept first. And who remembers how to solve that? When we have our y-intercept, that means we want to set x equals to 0. So we want to evaluate f of 0 and we want to solve for y. Okay, so let's go ahead and do that. So in this case over here, we have f of 0 equals to 0 minus 2 times 0 plus 3. So that was nice and easy. We can see that our y-intercept over here is simply 3. Okay, perfect. So what about our x-intercept? So x-intercept, we have to do the opposite and set y equal to 0. So for x-intercept, we are setting f of x equals to y equals to 0, and we want to solve for x. Okay, so in this case, what do we get? Let's look at our function here. So we have that 0 equals to x to the power of 5 minus 2x to the power of 4 plus 3. Okay, so here we can use different theorems like factor theorem, remainder theorem. I'm going to tell you right now that x equals to -1 works. But please, as an exercise, I want you to go through and practice the other techniques. I'll show you what this means here. So since I know that x equals to -1 by factor theorem and remainder theorem, if I plug this into my function, then I should get a remainder of 0. So let's see what that looks like. So that means I'm going to have -1 to the power of 5 minus 2 times -1 to the power of 4 plus 3. So that means I've got -1 minus 2 times 1 plus 3. So this equals to -1 minus 2 plus 3, and hey, that equals to 0. So that means that x equals to -1 is a factor. Okay. So I'm going to tell you right now that that's the only real factor here. So that means that we have that x equals to -1 is an intercept. Okay, so let's move on. So we've done the D, we've done the I, so now we have the S. And what is S? S is our symmetry. So we want to check if we have an even or odd function because that will help us determine whether we have line or point symmetry. So remember the check for an even function. We're checking if f of -x equals to f of x. Let's do that in our case. So we have that f of -x equals to -x to the power of 5 minus 2x to the power of 4 plus 3. What I did there was I just put a negative in front of my x. So I'll just do that actually once more for you, breaking down the steps. So we would have -x to the power of 5, then we'd have minus 2 -x to the power of 4, oops, there we go, plus 3, and following our exponent rules, we're going to get what we have above there. And we can see that this does not equal our original f of x. So that means that this is not even. And if it's not even, then there's no line symmetry. So that's kind of the mental process I want you to go through. First, check if it's even. If it's not even, then there's no line symmetry. Okay, now let's see. Let's check to see if it's an odd function. So we remember that odd function is negative f of negative x equals to f of x. So we already found f of negative x, so we're just going to put the negative in front of all of that. So negative f of negative x is equals to x to the power of 5 plus 2x to the power of 4 minus 3. And does that equal our original function? And just so you know, our original function for memory is f of x equals to x to the 5 minus 2x to the 4 plus 3. Nope, this does not equal to our original function. So this is, whoopsies. This does not equal to f of x. Therefore, it's not odd. And then no point symmetry. So again, follow that same train of thought. Okay, so it's not even and it's not odd. Now what? Well, that just simply means that we have no symmetry. I guess that's kind of sad, but it's okay. We can live. So let's move on to our C. So our C, again, that is our concavity and our critical points. So let's start by looking for our critical points. Do you remember we have to find the derivative, and we need to set our derivative equal to 0, and we need to solve for x to find our critical points. I'm going to call critical points CP. Okay, so let's go ahead. So remember, f of x equals to x to the power of 5 minus 2x4 plus 3. That means x prime, first derivative x, we can use power rule to solve this. And again, if you need some help with derivative rules, please make sure to check out my whole derivatives playlist. I have a whole crash course which goes through everything. And I also have individual videos that will help you with each technique, such as power rule, chain rule, product rule, and yeah, tons of videos there. So check them out for sure. Okay, so following power rule, we have 5x to the 4 minus 8x to the 3, and then plus 0. So what we can do right away is we can factor this. So by factoring it, we can take out an x cubed, and then we have 5x minus 8 left. And following our point up here, we're going to set this equal to 0 and solve for x. So that means we have x equals to 0, or I'll take a step back. We've got x cubed equals to 0 from this term. And then from this term over here, we have 5x minus 8 equals to 0. So that means that we get that x equals to 8 over 5. And then we also have here that x equals to 3. So we have two critical points over here. So let's also go ahead and look for our point of inflection. So remember, when we find our point of inflection, we need to set our second derivative equal to 0. So let's go ahead and do that. So that means that first we need to find our second derivative. So we're just going to take the derivative of our first derivative. So if we're using power rule again, we're going to get 20x cubed minus 24x squared. And now we're going to set this whole piece equals to 0. Okay, so let's factor this again. So we can factor out an x squared, and we can also factor out a 4. So what do we have left? We have 5x minus 6 equals to 0. And let's look at our two terms here. We've got x equals to 0. And we also have that x equals to 6 over 5. Okay, so now we see that we have x equals to 0 in two cases. So this becomes the big question, where is this point, is it a critical point, or is it a point of inflection? So this is where we now have to consult a number line and take a peek. Okay, So what I recommend everyone to do is once you have your critical points and point of inflection is to draw a number line and put them on it. So we know for sure that's 6 over 5. So again, this is a number line in x. We know that 6 over 5 is a point of inflection because it's only one. It does not show up previously, and it shows up with the second derivative, so it's considered a point of inflection. We have x equals to 8 over 5, and we know that this is a critical point because it shows up with our first derivative and not with our second derivative. And then lastly, we have x equals to 0. And we're trying to figure out, is this a critical point or a point of inflection? So this is where we want to use our second derivative test, because I said in order for a number to be a critical point, it has to have different signs of the second derivative on either side of the point. So if we plug in, let's say, a number between 6 over 5 and 8 over 5 into our second derivative, we see that our second derivative on this interval is going to be greater than 0. However, if we plug in a number between 0 and 6 over 5, like 1 for example, on this interval, we can see that our second derivative of x is less than 0. And now we want to plug in a number less than 0 into our second derivative, and we also get that our second derivative, if we take a number less than 0, is also going to be less than 0. Okay, so we're looking at between these intervals over here. We can see that between this point of inflection, our second derivative goes from being negative to positive, so that confirms that yes, hooray, this is a point of inflection. Our 0 over here, we can see that the second derivative is negative on either side, so that means this is not a point of inflection. That means that this over here is a critical point because the second derivative does not change. Okay, now let's go into our next step of classifications. We want to know, do we have a max or do we have a min at our critical points? Well, this is where we use the second derivative test. It tells us that if our second derivative is greater than 0, then we have a local min. So that means that this critical point is a local min. If our second derivative is less than 0 at a critical point, that means we have a local max. So that means this point, 0, is a local max. So now we've determined and we've classified all of our points. So make sure that you always do this step. We always have to double check if our points are truly critical points and truly points of inflection. Setting up our number line and using our second derivative to help us is really going to be critical. Don't mind the pun there, in order for this to work. Okay, so our very last step we have to do is check for asymptotes. In this case, it's actually going to be pretty easy. We've already determined that, well, this is a polynomial. And do polynomials have asymptotes? No, they do not have asymptotes. So this saves you a little bit here from having to find it. Polynomials do not have asymptotes, therefore there are no asymptotes that we have to sketch. Okay, so the last thing we've got to do is actually sketch our curve using all the information that we have, that we have just collected. So let's just try to draw out a little Cartesian plane over here that we can use. Please don't mind my squiggly lines. So we've got x and we've got y. Okay, so let's go and put all the points that we know. So we, first of all, let's start with our intercepts. So we know we have an x-intercept at -1. So that should be filled in. And then we have our y-intercept at 3. 3 up there. And what is our point of inflection? So this is where, let's go up to our number line and let's actually find the coordinates. So we have our x value, but let's find our xy coordinate. So when x is 0, we know that y is 3. When x is 6 over 5, I'm going to plug that into our original function. And I'm going to get approximately 1.34. And our last point here, I have 8 over 5, and when I plug that in, I get approximately 0.38. So now we have coordinates for all these. So that means I can simply plug them in. I'm going to have my point of inflection at, what do I have? 6 over 5, so 1 and a bit, and 1.34. So somewhere about here, let's just say this is 1 over here, this is 2, this is 3, somewhere about over here. And then I'm also going to have to make sure I have my local minimum at 8 over 5 and 0.38, which is going to be, let's say this is 1, this is 2, this is 3. My other point is going to be just about over here. And now let's connect the dots. So I'm going to go through this. I have my max at 3. Oops. Oh my goodness. There we go. So I've got my max at 3. I'm going here. I'm concave down. And now my point of inflection, I'm going to become concave up. And remember, our domain and range is all real numbers. So our function is going to look something like this. So at this point over here, this is our point of inflection. This is where it changes from concave down to concave up. Over here, we have this is our local max. Over here, we have our local min. And the reason why it's a local and not global extrema is that you can see from these arrows that they're going to continue up towards infinity. This is going up to infinity in this direction, and this one's going down to negative infinity in that direction. So technically our true global max and min is going to be infinite. That's why we should just show our local ones here, because that's what we can calculate. And yeah, we have our x-intercept, and then we also have our y-intercept here, which doubles as our local maximum. You can always plug in some other points of x in a table of values to help you get a few more values of y, so you have a few more anchoring points. That's always a good idea. And there you go. You've sketched your whole curve, and you've also optimized it because you know where your local extrema are. And yeah, with that, I want to wish you all good luck with your upcoming tests, and great job today following this tutorial. Please let me know in the comments if you have any questions. I look forward to helping you, and definitely subscribe for more videos. I can't wait to see you again.